Hello everyone, Mr. Linder here. Let's talk about resting membrane potential. So the resting membrane potential is really the separation of charge across the plasma membrane of cells. And it turns out that cells have resting membrane potentials anywhere from about negative 60 millivolts to about negative 85 millivolts. And so all cells of the body have this separation of charge, so they all have a resting membrane potential. But not all cells can change their resting membrane potential. Cells that can change their resting membrane potential, like neurons, skeletal muscle, cardiac muscle, smooth muscle, can then go on to do work using electrical signaling. But before we get into looking at electrical signaling along cells, we need to understand how this resting membrane potential is established. So the resting membrane potential is based on the distribution of positives and negatives. And it turns out that the outside of cells has both positive and negative charges, and the inside of the cell has both positive and negative charges. But the distribution of charges is not equal. It turns out that the inside of cells has more negative charges, and so the inside of the cell is going to be inherently negative. And the outside of cells have more positive charges, and so the outside of the cell has a more positive charge. And this is what we call the resting membrane potential, this distribution of charge across the plasma membrane. But where does that distribution of charge actually come from? Well, it comes from the movement of ions across the plasma membrane. Now, we can look at lots of ions. We can look at sodium, potassium, calcium, chlorine, etc., etc. But it turns out the main players in resting membrane potential are sodium and potassium. Potassium has a high concentration inside of cells and a lower concentration outside of cells. And sodium has a high concentration outside cells and a lower concentration inside of cells. So if you were to look at their natural diffusion, potassium would diffuse out and sodium would diffuse in. But that diffusion is based on channels in the plasma membrane of cells. So depending upon the number of channels that you have in the membrane, that will dictate the permeability of both sodium and potassium. Now, if you just let sodium and potassium diffuse, they're going to reach equilibrium. And if we reach equilibrium, then we can't really do work with those cells. So in order to prevent equilibrium from taking place, we know that cells spend energy in order to pump sodium and potassium against their concentration gradient. So it turns out we use the sodium-potassium pump to move sodium back to the outside of the cell and to move potassium back to the inside of the cell. But of course, that takes energy to do that. So we actually spend energy to maintain the resting membrane potential. But that spending of energy creates this disequilibrium across the plasma membrane so that some cells can do work. So it's okay to spend energy if we're going to establish the resting membrane potential so that we could use some cells in the human body to do work with that resting membrane potential. So where does this, though, resting membrane potential come from, and how do you really establish this? Well, to dive deeper, you have to look at driving forces that affect the movement of ions across the plasma membrane. So first off, we want to talk about chemical driving forces or concentration gradients. So a chemical driving force is really just when you have a high concentration and a low concentration, and you see movement down the concentration gradient. So in this example, it's showing a high concentration of positive charges inside of the cell and a lower concentration of those positive charges outside of the cell. So that is a chemical driving force. There's a force, a diffusion, from high to low concentration. If you were going in the opposite direction, right, that would be an uphill movement. So that would be up the concentration gradient, low to high, and that of course takes energy. To move potassium back into a cell, it takes energy to do that. Just like to move sodium out of the cell, it takes energy to do that. So a concentration gradient is a chemical force. And so ions have a chemical force. They have a concentration gradient. Ions, though, also have an electrical driving force. It turns out that there's electrical attraction. Because there's an unequal distribution of charge between the inside of the cell and the outside of the cell, the inside of the cell has this negative charge, and the outside of the cell has a positive charge. And so when you look at ions, you should understand that opposites attract. It's a chemistry concept. So something that has a positive charge is attracted to negative, and something that is a negative charge is attracted to a positive. Opposites attract. So in this example, here we have some positive ions that are being attracted to the inside of the cell because the inside of the cell is negative. And that force is considered the electrical driving force for that particular ion. So this could be sodium being attracted to the inside of the cell. But potassium is also attracted to the inside of the cell. And so what you may notice from this is that when you look at potassium's chemical driving force, it's directed to the outside of the cell, but its electrical force is directed to the inside of the cell. They're actually working against each other. For sodium, you have electrical attraction to the inside of the cell, and you also have concentration gradient or chemical driving force to the inside of the cell. So they're actually helping each other. When you have both an electrical and a chemical driving force, you can actually combine those forces together to form what's called an electrochemical driving force. So an electrochemical driving force applies to ions because ions have both a charge and they have a concentration gradient. And so you can add together these forces. You can add the forces, both electrical and chemical, and you can have this electrochemical driving force. And that electrochemical driving force affects the movement of those ions across the plasma membrane. And the movement of the ions is what's going to establish the resting membrane potential. So what is this membrane potential in general? A membrane potential really is just the difference in voltage across the membrane. If you could take a voltmeter and you could read at the level of the cell, right? If you could shrink yourself down to the level of a cell and you could place a voltmeter inside and outside across the membrane and you could read the membrane potential, you would get some number. And you may recognize negative 70 millivolts. That happens to be the resting membrane potential for neurons. But really, it's just the voltage across the membrane. And because it's an unequal distribution, we have the negative charge on the inside, we have the positive charge on the outside. And so for convenience, we always denote the charge on the inside of the cell when we are listing our resting membrane potentials. So we list it as negative 70 millivolts across the membrane. But again, membrane potentials will vary from cell to cell. Negative 70 millivolts is for neurons. Positive ions are attracted to the inside of the cell. Negative ions would be repelled by the inside of the cell. Okay? Because something like chlorine that has a high concentration outside of cells might have a chemical force going in, but its electrical force would be to the outside. And so again, there's opposition to that movement. And that's why we have this idea of an electrochemical driving force. Now, not all molecules are going to have an electrochemical force. If you took something like glucose, a non-charged molecule, is not going to have an electrical attraction. It's going to have a concentration gradient, so you can talk about its chemical force, but you don't have to talk about its electrical force because it doesn't have a charge, and therefore there's no electrochemical driving force. Electrochemical driving forces are reserved for molecules and ions that have a charge. Now, the direction of the electrochemical force will be based on adding the vector quantities together. A concentration gradient, an electrical attraction, these are really what we call vector quantities. Vectors are forces that have direction and magnitude. So if you want to know what the electrochemical driving force is, you would have to add the forces together. So for example, if you have sodium concentration gradient and sodium electrical gradient, both directed towards the inside of the cell, we could add those two vectors together to come up with an electrochemical force. And notice the arrow gets bigger because you're adding those two forces together. What if chemical and electrical were equal and opposite to each other? Well, then they would cancel each other out and you would have no electrochemical driving force. They would cancel each other out. You would essentially be at equilibrium. So we can actually use equations to determine what the equilibrium potential is for a single ion, because we can actually measure what the resting potential of the cell would have to be to create an equal and opposite concentration gradient versus electrical attraction, so that we would get an equilibrium situation. In order to get an equilibrium potential, we use something called the Nernst equation. So in this scenario here, what you're looking at is the equilibrium scenario for potassium. Potassium has an equilibrium, so the equilibrium of potassium is equal to negative 90 millivolts. So what does that mean? It means that the resting membrane potential would have to be negative 90 millivolts in order for the electrical attraction to be equal and opposite to the chemical driving force. So remember, you have potassium in high concentration inside the cell, low concentration outside of the cell. So you have a concentration gradient towards the outside. The inside of the cell would have to reach a negative 90 millivolt resting membrane potential for the electrical attraction for potassium, the electrical driving force, to be equal and opposite to the chemical force. So these two lines line up. And so that would give us a 0 electrochemical driving force. Okay? Now, we don't want that to happen. Okay? Equilibrium is not something that we're shooting for. But understanding equilibrium allows us to predict what resting membrane potentials would be for given cells. If we can take the main ions, sodium and potassium, and we can determine what their equilibrium potentials are, essentially what that gives us is that gives us the range at which resting membrane potentials fall for all cells in the human body. And it turns out, again, resting membrane potential for potassium is going to be negative 90 millivolts. Resting membrane potential for sodium is going to be on the positive side. So we're going to be up here. Some books say positive 60 millivolts. Others, I've seen positive 66 millivolts. It depends on what concentrations you use when you calculate using what's called the Nernst equation. So when we look at the major ions, the major players in resting membrane potential, we can use this Nernst equation to figure out what's called the equilibrium potential. So what is, by definition, what is it? The equilibrium potential is this hypothetical membrane potential where the electrical driving force and the chemical driving force are equal and opposite to each other. So if the membrane potential was actually the equilibrium potential, you wouldn't have spontaneous movement of the ion that you're measuring. When you have negative 90 millivolts as your resting membrane potential, then you no longer have spontaneous movement of potassium. For every ion that came into the cell, there would be another ion that's moving out of the cell, and you would be at equilibrium. So again, equilibrium is not something that we shoot for. We prefer homeostasis in the human body. We want resting membrane potential, but knowing negative 90 and eventually knowing positive 60 for sodium, we know that resting membrane potential is probably going to fall somewhere in between those. And it turns out again that it's somewhere between about negative 85 and negative 60 millivolts for all cells of the body. So how do you calculate this hypothetical resting membrane potential? You use what's called the Nernst equation. So again, remember, this is a theoretical situation. Okay? When you have the same electrical force to the chemical force, you have reached equilibrium for that particular ion. So it's really a stabilizing potential. Negative 90 millivolts for potassium is a stabilizing potential. How do you calculate that? You use this equation called the Nernst equation. And so this is what the Nernst equation looks like. We have E of some ion. We're going to start with potassium. Equilibrium of potassium is equal to 61 divided by Z. Z is the charge of your ion times the log of the concentration outside divided by the concentration inside of the ion that you're looking at. So you would have to know the concentrations for the ions that you're working with. Turns out that there are tables that we can use. So for example, if we were looking at potassium and we wanted to utilize the Nernst equation to determine that equilibrium is negative 90 millivolts, then we could use concentration inside the cell, 150, concentration outside the cell, 5 millimolar. And so by using the Nernst equation, we can plug in the values and we can find out what the equilibrium potential for potassium really is. So let's go back and take a look at that equation. Let's do equilibrium for potassium. So what is the concentration outside of the cell? Well, the concentration outside we know is low. Okay? When we look at a typical situation for human cells, high potassium inside, low potassium outside. So we're going to use the 5 millimolar concentration outside, and we're going to use the 150 millimolar concentration inside. So our equation looks like this. Equilibrium of potassium is equal to 61 divided by the charge of potassium. Well, the charge is plus 1 times the log concentration outside, 5, concentration inside, 150. And so if you work this out on your calculator, you're going to get negative 90 millivolts as the equilibrium potential for potassium. And again, what does that tell you? It tells you that the chemical driving force and the electrical driving force are equal and opposite. Again, not what we're shooting for, but it's a good theoretical value to know so that we know one of the bookends for where resting membrane potential is going to fall for cells. If you can't shrink yourself down to the size of a cell, right, and measure the voltage across, right, we still know it's not going to be at negative 90 millivolts because that's equilibrium for potassium. What if we did the Nernst equation for sodium? Same idea, equilibrium for sodium, but you need different values for concentration outside and concentration inside. Turns out that sodium is high concentration outside and low concentration inside. So the concentration outside is, we'll say, about 150 millimolar, and the inside is about 15 millimolar. You can look it up in the tables. So same equation, 61, divided by the charge, same charge because sodium is also a +1, times the log, concentration outside, 150, concentration inside, 15. And so if you plug that into your calculator, you're going to get approximately plus 60 millivolts. Now again, if you change these values a little bit, the concentration inside and outside, you can get slight variations in the equilibrium potential numbers. But again, what it does is it tells us that the cell would have to be a positive 60 millivolts for its resting membrane potential. So basically the cell would have to flip, right? The inside would have to be positive and the outside would have to be negative in order to create a scenario where you have equilibrium for sodium. Because sodium has a chemical gradient to the inside, and in order to flip the electrical gradient, be attracted to the outside, the inside of the cell has to become positive 60 millivolts. Okay? So equal and opposite, they cancel each other out. You have a 0 electrochemical force, and that's equilibrium for sodium. So we have equilibrium for sodium, we have equilibrium for potassium, and resting membrane potentials fall in between. Because again, these are the major players for establishing resting membrane potential. It's not to exclude calcium and chlorine and other ions, but these are the major players when you're talking about establishing resting membrane potential. So to summarize, where does this resting membrane potential come from? How is it that the resting membrane potential for a neuron is this negative 70 millivolts? Here's the voltmeter on the inside, voltmeter on the outside. We see the negative charges on the inside, positive charge on the outside. Again, there's both positives and negatives everywhere, okay? But there's more negatives on the inside and more positives on the outside. How does this come to be to give us this disequilibrium that gives us a resting membrane potential? How do we generate this resting membrane potential? So within a cell, things to consider. Inside of a cell, you're going to have fixed anions. So inside of the cell, there are fixed proteins, there are fixed phosphates, nucleic acids, okay? And those are inherently going to have a negative charge. So the inside of the cell really is already negative. The fixed anions are going to attract positive cations to the inside of the cell. There's already going to be an electrical attraction to the inside of the cell. So fixed anions are attracting positive charges to the inside of the cell. The cell is permeable to both potassium and sodium, but it's not equal. It turns out that cells are about 40 times more permeable to potassium than they are to sodium. So which ion really plays the bigger role in the resting membrane potential? It turns out it's potassium. Potassium is going to play the bigger role. And why does it play the bigger role? It's more permeable. There's more channels in a membrane for potassium than there are for sodium. So if we were to draw in channels in the plasma membrane of a cell, the majority of them would be labeled potassium. Most of them would have a potassium label. Okay? And then every once in a while you'll have a sodium. Okay? So cells are just inherently more permeable to potassium than they are to sodium. And so that's also why when you look at where resting membrane potentials fall, negative 90 being the bookend because that's potassium's rest or equilibrium potential, and positive 60 being the bookend for sodium, you notice that resting membrane potentials fall closer to potassium's equilibrium. Why is that? Potassium plays the bigger role, right? Potassium is more permeable. And if potassium is more permeable, then resting membrane potentials are affected more by the movement of potassium than they are sodium. So cells are permeable to both sodium and potassium. Both ions move according to their concentration gradients and their electrical attraction. Potassium leaks out of the cell, sodium leaks into the cell. But as positive ions are moving, you're going to establish a more negative charge inside of the cell because there's more potassiums moving out, or we should say leaking out, than there are sodiums coming in. And so the inside of the cell is already negative, and you're losing these positively charged potassiums to the outside, and so the inside of the cell is becoming more and more negative. As the inside becomes more negative, though, that's going to help pick up the electrical driving force for sodium. So sodium's going to move a little bit better as the inside of the cell becomes more and more negative because, again, opposites attract. So that sodium electrochemical force is gaining some momentum as the inside of the cell becomes more and more negative. And so as that happens, you're going to see a slowing down to some degree of potassium and a speeding up of sodium. So potassium movement begins to slow, sodium movement begins to increase, and eventually what you're left with is a steady state scenario that takes place, right? So we get this uneven distribution of ions across the membrane, but they reach a steady state. They don't reach equilibrium, right? We're not talking about equilibrium for potassium and equilibrium for sodium. Those are the bookends, but we're going to reach some steady state, and that's going to be the resting membrane potential. And for neurons, it's negative 70 millivolts. So because the membrane is more permeable to potassium, the resting membrane potential ends up being a lot closer to potassium's equilibrium potential. If we left this unchecked, then of course the leakage would lead to equilibrium, and we don't want that to happen. So we spend energy using the sodium-potassium pumps to ensure that we maintain the concentration differences of sodium and potassium so we can keep the leakage of sodium and potassium going, and that allows us to maintain the disequilibrium and thus the resting membrane potential. So the sodium-potassium pump spends energy. It pumps 3 sodiums out for every 2 potassiums that come in, and this maintains the concentration gradients so that we can keep sodium and potassium moving across the plasma membrane of cells. Now again, it's important to note that we're not talking about just sodium and potassium. There are other ions involved in the resting membrane potential. And there's a famous equation, it's called the GoldmanHodgkins Equation, that actually takes into account multiple ions rather than just the Nernst equation looking at one. So this is the GoldmanHodgkins Equation, and this is voltage of the membrane. So Vm here, voltage of the membrane. And what you'll notice is that it takes into account not just one ion at a time, but multiple ions. So here we have potassium, sodium, chlorine. And not only does it take into account their concentrations, right? So the brackets represent concentrations, but it also takes into account what are their permeabilities. So what is the permeability of that particular ion? And again, that goes back to how many channels does the membrane have for a particular ion. The more channels, the more permeable that ion will be. So the Goldman-Hodgkin cats can actually predict what the resting membrane potential would be by looking at multiple ions at a time. The Nernst equation only looks at one ion at a time. So in summary, what is the resting membrane potential and what are some key factors to remember? Probably number one, that the concentrations or the concentrations across the plasma membrane need to be established. So there needs to be a concentration difference across the plasma membrane. And number two, there has to be permeability to ions across the plasma membrane. And those two key factors are going to help determine what the resting membrane potential is going to be. So I hope that helps. Take care.